Hello everyone, welcome to my class. Today we are covering section 6.2, volume by slices. So let me start the class right away. So far we have learned to find the area of two-dimensional regions using definite integrals. So the formula is area equals to the definite integrals of fx from a to b. So here's fx, it's a height, so we integrate the height over ab. This gives us the area. Now we'll study finding volume of three-dimensional solid region using the definite integrals, where the formula is v equals to the definite integrals of area functions from a to b. So here we are integrating area functions. In the previous formula we are integrating the height. Great. In these sections we will find the volume by slices in two ways: disk method, washer method. First, let's try to answer these questions. How we generate a three-dimensional solid? So the one way of generating a three-dimensional solid is by rotating an area around the axis of rotations. For example, rotate a semicircle around its diameter, we get a sphere. Rotate a rectangle around one of its edges, we get cylinder. And we know the volume of cylinder is pi r square h. In these sections, we denote the solid by uppercase letter S. Now let's talk about a disk method. Disk method. In disk method, each cross-section of a solid is a circular disk. So let's consider a functions fx defined on closed interval ab, and rotate the regions under the graph of f bounded between x equals to a and b around the x-axis. And suppose our function is constant. Then let's rotate this region around the x-axis. Then we'll get the solid here. The solid is a cylinder. So the idea is take a stripe and swing that stripe around the x-axis. Then that gives us this cross sections here on the solid. That's a circular disc, and we can do the same for each of the stripe here. That means at the end we are revolving all of this area, so this gives us this circular cylinder. Then to compute the volume, let's first find the area of this cross section. The cross section is a circular disc, so its area is simply pi radius square. Radius is the distance from axis of rotations to the outer surface of the cylinder, so which is simply fx. So then pi r square becomes pi fx square. So thus the volume equals to the definite integral of pi fx square from x equals to a to b. Great. So here what we did to compute the volume of the cylinder here in this particular case, we chopped the cylinder into tiny slices, and then we approximate the volume of each slices, and then we add them up. Great. So now in case B, suppose function is not constant functions. So here's this is my functions, and let's rotate this region under the graph of functions above the x-axis bounded between x equals to a and x equals to b around the x-axis. Then when we rotate this region, then our solid is this one, the diagram on my right side. So this width of this stripe is dx, and then the cross section will be circular disc again. So then first find the area of the circular disc again, which is pi radius square. Radius is the distance from the axis of rotations to the outer surface of this solid, which is this height, or this height, which is this fx. And to find the volume, we need to integrate. So we need to integrate, then v equals to definite integrals pi times fx outside square from x equals to a to b. I hope this makes sense to you all. Now let's move on. Similarly, we can rotate the regions around the y-axis. Then the volume formula will be v equals to, so this times my radius is a function of y, so pi r is a function of y, so pi r square becomes pi f of y outside square, and we are rotating towards y-axis, so then I'm integrating with respect to dy, so then limit of integration is y equals to c to d. Great. Similarly, now let's talk about washer method. In washer method, our cross section is a hollow circular disc. So consider two functions and rotate the regions bounded by these two functions around the x-axis. So again, suppose our functions are constant, the case number A, then f function is this one, g function is this one, and let's rotate this region between the f and g functions around the x-axis. So the idea is take a stripe on that regions and swing that stripe around the x-axis. Then this generates this circular cylinder again here. Our cross section is a hollow circular disc. So first let's find the area of this hollow circular disc and then integrate. So area of a washer slice is area of the full disc minus area of the hollow. So we are only rotating this piece. So that means I need to throw this hollow part out. Then area equals to pi outer radius square minus inner radius square. So that means the area of the washer is area of the outer circle minus area of the inner circle. So outer radius is the distance from x-axis to the outer surface, means the functions fx. Just fx gives us the radius, outer radius of the circle, and for the inner circle's radius, the g function gives us the inner circle's radius. So then pi times f square minus g square. So the volume is definite integrals of pi f square minus g square, integrals from a to b. I hope this makes sense to you all. And now case B, suppose our functions are not constant functions. That means let's say our f function is this functions, which is kind of a diagonal functions, and g function is this one here, which is maybe y equals to x cubed functions. And now we are talking this region bounded between f and g. And let's rotate, let me scroll down. Let's rotate this one, this region around the x-axis. Then this generates this solid here. So I hope it at least you can visualize that solid here. Then our volume formula is definite integrals a to b pi times outer radius square minus inner radius square. So here outer radius is again given by outer functions fx, and inner radius is given by inner function, which is gx. So this is our formula. Similarly, we can rotate around the y-axis. So at that times, my volume formula is definite integrals of a pi, then radius is function of y here, so f square y minus g square y, and we are integrating with respect to y, so y limits from c to d. Great. Now quick remark, similar idea will work for different axes of rotations other than x and y axis. So I mean, for example, here we can rotate these regions between fx and gx maybe towards, let's say, y equals to -5 or x equals to -2. Great. Note that in both disk and washer method, the cross sections are taken perpendicular to the axis of rotations and the solid has been decomposed into a stacked circular disk. So yes, our cross sections are taken as a perpendicular to the axis of rotation here. This is the axis of rotations, and we take a cross sections here which is perpendicular to the axis of rotations. Great. Now let's do some example. Example 1. Find the volume of the solid generated when the regions under the curve y equals to radical x between x equals to 0 and x equals to 2 by rotating once about the x-axis, second once about the y-axis. So then how to start? So let's sketch the region. Again, we are using first the disk method. So our region is here. So our function is y equals to radical x. This is my y equals to radical x. And then between x equals to 0, between x equals to 0 and x equals to 2, this one. So this region under the graph of y equals to radical x toward the x-axis. So then take a stripe and swing this stripe around the x-axis. So this generates this circular disc, right? And same way circular disc here, circular disc here. So that means we are stacking circular disc. So the solid looks like to me a kind of a headlight shape, or I don't know, it's a vessel shape. Awesome. So then let's use our disk method. So volume equals to our stripe width is dx, so we are integrating with respect to x. So then dx there. So the volume equals to definite integrals x limit x equals to 0 to 2 pi, then radius is square. Our radius is this height from axis of rotations to the functions here. So this function is simply y equals to radical x. So we are using y, that is radical x square here. So I hope this makes sense to you. So then volume equals to definite integral 0 to 2, then radius is y is radical x, so radius is square, it means radical x is square dx. Great. Then the next step, let's cancel this square and then the radical. So we have pi, then definite integral of x is simply x squared over 2, and put the limit 0 to 2 and simplify. This gives us 2 pi. So the volume of this solid is simply 2 pi. Great. Now let's rotate this about the y-axis now. So now this times we are taking this stripe, because this is the region here. The region is here about the y-axis, means this is the y equals to radical x, and between x equals 0 and 2, now I need to find out the corresponding point for y. So when x is 0, y is 0. When x is 2, y is radical 2. So then here, so then 0 to radical 2, and we are taking the stripe here, so whose width is dy, and then we are swinging that stripe towards the y-axis. Okay. So then this whole region, so when I rotate toward the y-axis, it gives us this shape here. It's kind of a more flat cone, right? So then what's our formula? So then volume equals to definite integrals. We are integrating from y equals 0 to radical 2 pi r square dy. What is my r? Our radius is this distance. So this distance is x, either here or here or here. So this is x square dy. What is our x? Y equals to radical x. So solve for x equals to y square. So then y square square. So I hope this setup makes sense to you all. Then we can easily integrate this into again functions. So then the last step here, pi as it is, y square, this square is y to the power 4. The integration of y to the power 4 is y to the power 5 over 5, and then limit 0 to radical 2. then put y equals to radical 2 and take power 5 and simplify. It gives us 4 without radical. So the last line here, pi as it is, y to the power 4, integration of y to the power 4 becomes y to the power 5 over 5, and limit from 0 to radical 2. Put y equals to radical 2. So radical 2 to the power 5 is 4 times radical 2 over 5 times pi. So that's a typo here. So let me hide it. There is no radical 5. So our final answer is 4/5 radical 2 pi. Great. Now let's move on. Let's do example 2. Find the volume of the solid generated when the region bounded by the curves y equals to x cubed, y equals to x, and x is greater than or equals to 0, rotated about the x-axis. So here I do have two functions, so we are using Wasser method. So let's begin the solution. Let's try to sketch the region here. Y equals to x cubed is this curve. Y equals to x is this diagonal line. X is positive, means I'm in the here first quadrant. So we are rotating this region bounded between these two curves around the x-axis. So then take a stripe here. This stripe's width is dx. So we are integrating with respect to dx. Then when I swing this stripe around the x-axis, so this generates this solid. I hope this solid makes sense to you all. So first let's find the intersection point, because I do need intersection point for the definite integral. So solve x square equals to x, put this to y equal, then bring this x to the left side, so x cubed minus x equals to 0, factor x out, so x square minus 1 equals to 0. So the product of two numbers equals to 0 is either 1 should be 0, so either x equals to 0, or x square minus 1 equals to 0, so x equals to plus minus 1. So the intersection points are 1 is 0, 1 is plus 1, and 1 is minus 1. So, but here we're not interested on minus 1. So we are only using 0 and 1. Awesome. So then Wasser methods, the volume formula is v equals to the definite integrals from x equals to 0 to 1, then pi times outer radius square minus inner radius square. So outer radius is given by this y equals to x, and inner radius is given by y equals to x cubed. So then x square minus x cubed square. Then you can easily integrate pi as it is. X square integration becomes x cubed over 3 minus x to the power 6. Integration becomes x to the power 7 over 7, and limit from 0 to 1. So plug the value x equals to 1 and simplify. So this gives us the volume is 4 pi over 21 in cubic unit. Great. Now let's do example 3. So this time our axis of rotation is different than x-axis and the y-axis. So example 3, find the volume of the solid generated when the region in first quadrant bounded by the curves y equals to x square, y equals to 4, and x equals to 0, rotating about the line y equals to negative 2, about the line x equals to negative 2. Great. So let's sketch. So here's how we have two curves. So we are using Wasser method. So let's sketch the region here. That's better. Y equals to x square is this parabola here. And we are interested in first quadrant, so I don't need to draw this part of this parabola. So I only draw this part. So y equals to x square, y equals to 4, this horizontal line, and x equals to 0, this y-axis. So we are talking about this region here. So we are rotating these regions around the line y equals to -2. Y equals to -2 is down here. So this whole regions we are rotating around the line y equals to -2. Okay. So the idea is we are drawing the stripe here. This stripe is perpendicular to the axis of rotations. So its width is dx, so we are integrating with respect to dx. So now, in Wasser method, I do need first the limit for our x value here. So our y equals to 4, so solve these two equations, put y equals to 4, then x squared equals to 4 means x equals to 2. So we have 2 and 0, so x limit are 0 to 2. Then I do need to find the outer radius and the inner radius. So outer radius is the distance from axis of rotations to the outer curve. So here the distance from here to here is 4 and then 2. 4 plus 2, 6. And the inner radius is the distance from axis of rotation to the inner curve. So from here to here, which equals to from y equals to -2 to x-axis is a 2. And then from x-axis to the inner curve, which is simply y is x squared. So x squared plus 2 is our inner radius. Okay? So then let's begin the solutions. So volume V equals to definite integrals from x equals 0 to 2 pi times outer radius. So outer radius is again one more time the distance from axis of rotations to the outer curve. So from y equals to -2 to all the way to y equals to 4 is 6. So 6 is square. So this one and this one. And then minus from formula. And inner radius is the distance from axis of rotation to the inner curve, which is from y equals -2 to x-axis is 2. And from x-axis to the inner curve is y. That is x squared. So x squared plus 2 is square. I hope this setup makes sense to you all. Then now let's simplify and then take the integrations. So pi as it is, I can pull the pi outside the integral. 4 plus 2 is 6 is square 36 minus then multiply x squared plus 2 times. This gives me x to the power 4 then plus 4x squared plus 4 and then distribute this minus. So this becomes all of these are minus. Let's take the integrations. So pi as it is. Integration first we subtracted 4 from 36. So we have 32. Then take the integrations. Great. So then integration of 32 is 32x. Now minus x to the power 4 becomes x to the power 5 over 5 minus 4 as it is. X squared becomes x to the power 3rd over 3. So 4/3 x cubed. Put limit 0 to 2. Now put upper limit x equals to 2 and then lower limit 0 and simplify. Then we get 704 pi over 15. So that's the volume of this solid generated by these regions bounded between these three curves. Awesome. Now in part B, we want to rotate about the line x equals to -2. So now my axis of rotation is here, x equals to -2. So we are rotating parallel to the y-axis. So what's the idea? We take a stripe perpendicular to the y-axis, means this way. Then we are flipping that, we are rotating that regions towards this way, x equals to -2. So that means I do need a y limit. So for the y limit, let's find the y values here. So when x is 0, y is 0. Y is 0 means again origin. When x is 2, then this point is y is 4. So this point is 4. Then my limit of integrations will be 0 to 4. I hope it makes sense to you. Now let me go to the part B. Yep, y 0 to 4. And now we have totally different solid here. Okay, so our region is this one, y equals to x square, y equals to 4, and x equals to 0, these regions. Now we are rotating around the x equals to -2. So now take this stripe here, whose width is dy, and we are rotating around this line x equals to -2. So then this generates this shape here. It's a kind of a nice bowel shape. Okay. So then again we are using washer method. So then let's find the volume then. So volume V equals to the definite integrals y equals to 0 to 4. So 0 to 4. Then pi. Then what we need? We need outer radius square minus inner radius square. So now my radius is x value here. So the distance from this axis of rotations to all the way to the outer curve, that gives me the outer radius. And for the inner radius, the distance from axis of rotations to the inner curve. Now first let's talk about outer radius. So outer radius distance is from x equals to -2 to all the way to this parabola, y equals to x square. So this distance equals to first this distance, which is a fixed 2, right? This is the fixed 2 here. So this is the 2 unit. And I mean now we reach y-axis. From axis of rotations to the y-axis is the 2 unit. And from y-axis to the parabola is just the x, right? Are you following me here? So the total distance, that means outer radius, is 2 plus x. What is x? Solve these equations for x. So x equals to radical y. So then radical y plus 2. Radical y plus 2 square. I hope this makes sense to you all. Similarly, for the inner radius is the distance from axis of rotation to the inner curve. Inner curve is y-axis. So this distance is simply 2. So the 2 square. Great. So now just the routine computations. Pull the pi outside the integral. So pi times the definite integral 0 to 4. Then FOIL this radical y plus 2 outside square. Means multiply radical y plus 2 times. This gives me y plus 4 radical y plus 4. And then this minus as it is. 2 square is 4 outside dy. Cancel 4, and the next step, integrate. So pi as it is. Y becomes y square over 2. 4, just copy 4. Then radical y is same as y to the power 1/2. Then take the integral of y power 1/2. So it becomes y power 1/2 plus 1 is 3/2. And divided by 3/2. But dividing by 3/2 is same as multiplying by 2/3. That's why this 2/3 is there. Times y power 3/2. And the limit is 0 to 4. So put y equals to upward limit 4 and lower limit 0. Simplify. It gives us the volume is 88 over 3 times pi. Awesome. So with this example, we finish these sections. So in next sections, we will cover cylindrical cell method in section 6.3. Thank you.